So today I'd like to talk about an adaptive framework for optimization and prediction of ATM subsystems with machine learning, work which we've done the last 3 to 4 years at the German Aerospace Center in Brunswick, and also as joint work with, on the one side, with Samir Alam, who will talk in this session later this afternoon, and with Michael Schulz, who used the machine learning prediction models for his boarding simulations. So some corporations are influenced this work here on this framework. So what I want to talk about, the basic idea of a framework of the machine learning process here in my scope of the work is to apply supervised models to performance data in ATM systems. So on the one side, as you can see here on the upper picture, we have a continuous system of the reality, and when we measure the systems with certain metrics, or for example performance indicators, key performance indicators, we get a secret value at a certain point of time t of the system. And what we wanted to achieve is to create predictors to say, okay, what will happen about 2 steps further in the future. How would one certain performance indicator, for example, behave in the future, like delay of departures or delay of arrivals. This is why we created an adaptive framework to comprise several steps of the application of neural networks for the data processing and so on. So in the first step, I'd like to show some basic concepts of this performance-based airport management systems, and we also like to talk about the interdependencies, the linkages between different factor stakeholder subsystems within the ATM. In the second step, I'd like to show the framework, which consists of 3 main components, which is the system identification, the simulation, and the control. In the third step, I show you some experimental results, and we close this up with a summary and the outlook at the end. So in the first step, when we talk about performance-based airport management, we talk about the measurement of different processes, of different participants of the air traffic system. So we talk about the stakeholder performance at a different point of time, like airport, the airline, air traffic control, ground traffic. There are different performance-based concepts. The most common one is the ACDM, and we also take a closer look at future ideas of this concept, like total airport management and the overall performance-based airport management. As you can see here, such concepts comprise different parts of measurements and different parts of influential factors within this analysis, like schedules, which are some kind of, or we can interpret as the demand in our system. We have the capacity of the infrastructure of the airports in our analysis. We have the weather data, which may influence the capacity and also the performance of the system at all. And we have the ATM performance including the delay values, how a system can react to certain schedules, to certain capacity restrictions, to certain weather conditions, and perform flights at an airport. So when we break this down to the common ACDM, or airport collaborative decision-making systems, we have different milestones for every single flight. As we can see here, this 16 milestones are showed up, and in our analysis with our data, we reduce the analysis to the main components, or the most important parts of these data, which is here, for example, for a whole flight, we can check up the delay, for example, for the arrival, and for the demands, we can take a look at the in-block and the off-block times within these ACDM data. We call this a macroscopical approach. So we take a look at the whole, or take a look at all flights of the whole airport and can reduce these analysis to this in-block and off-block times. When we say we go more deep into one single process, for example, the boarding as part of the turnaround, we can interpret this as a microscopic approach. So we take one certain step or one certain procedure of this ACDM milestone approach. Michael Schulz talked about the boarding procedures and the boarding prediction with machine learning a few years ago here in this session, so I don't want to go deep into the boarding themes, more like the in and off block predictions. So if we have our data, our ACDM data, we know we need to focus on the in and off block times, and we need to create some kind of a system which understands the behavior of these times for every flight. So we split our framework or our application for neural networks into the three parts I mentioned before: the system identification, the simulation, and the control. And they all depend on of the availability of the input and output sets, and depend on the availability of the model itself. So we call a neural network which is able to map some input data to the output data, which means the demand, the schedule data, the weather data, to a delay, and we call this a virtual ATM system. So this is just a trained neural network in this case. And the first step, the system identification, we need to create this virtual ATM system, which means we take some historical data, like flight schedule data and weather data of the past, put them into the neural network, and create or try to map these data to certain delays, which we also received as historical data. So this is the first step. In the second step, we like to take this trained model, this trained virtual ATM system, take into account, for example, the current current demand data or the current schedules and forecasts of the weather data, use this trained virtual ATM, and predict the delay values of a certain airport or certain flight. So this is the part of the simulation. And the third part is some kind of a reverse engineering. We take the trained model, and we know we want, for example, to reduce the total delay at an airport, and we want to achieve some optional schedules, changed schedules, to say, okay, with this changed schedule, under considering different restrictions, we are able to reduce the delay, for example, by 5% or anything like this. So we use the model and derive some behavior of the model itself. So let's take a look at our applications for our experimental results. In the first step, as I mentioned before, the boarding took place of Michael. We used his boarding simulation. With this boarding simulation, we were able to create 150,000 data sets of different boarding strategies, which we could also capture or measure by a certain complexity metric, for example, the progress of the seat load factor, and we could use this as an input data to predict the boarding process of an Airbus A320, which showed really good results here as application for the machine learning process application. The second part, the second application, is the so-called ATFM scenarios for the Airport Hamburg and London Gatwick. We used performance and weather data, ACDM data, from the years 2012 to 2015, which comprised around about 12,000 for Hamburg and 64,000 flights for London Gatwick. These data were measured as 12 ATFM KPIs, so we have 12 operational features for the airport side and 6 or 12 weather features for the weather side. I'd like to explain the weather features here in another slide. Why 6 and 12? Well, we can measure the weather with different scopes of interest. So on the one side, we have the meteorological aerodrome report, which is some kind of a historical description of the weather. We have many influence factors and many features. Some of them are important, some of them are not important. This is a very complex metric to use in this macroscopic view at an airport. On the other side, we have the terminal aerodrome forecast, which is some kind of a prediction of the weather with a predictive horizon of 60 hours, which means when we measure our data every 30 minutes, this is our measurement progress or our time slot, we have 12 time slots for these forecasts, which we can use for our simulation and control aspects. So these are very complex data, and we wanted to reduce the dimension of these weather data as input sets, so we applied the ADMAP score, which means the Air Traffic Management Airport Performance Score, which is some kind of a labeling or categorization of weather data. We receive 5 different ATMAP scores for a weather class and 1 total score, so 6 at all. And we can use these classified weather data as an input set to reduce the dimension of the weather factors in comparison with the operational factors like the demand and the number of departures and so on. And using this ATMAP score, it is quite easy to distinguish between good and bad weather days, as the example shows here for Hamburg. If you have an average value, ATMAP total value, above 1.5, you have a bad weather day, and below 1.5, you have a good weather day. So this is a good hint for us to split our data sets for our machine learning applications. So let's jump into the framework itself. The framework comprises different steps using this data I have mentioned, so the ATMAP score as well as the different KPIs for the operational features. And in the first step, we need to say, okay, what is our system selected? What is the problem we want to, or what is the defined problem? Which data do we have? What's the data scope? So if we have the data in the second step, we need to do some preparatory actions, which means we have to get an impression of the data we have. Maybe we need to clean this data up considering measurement errors and so on. And we need, it's very important to select our features and split our data for the final supervised learning, machine learning application to get the most important features for this application and to, use the most useful data here for this approach. The third step is to choose a model which is capable doing this application we want to do, this prediction of the delay values. So we need to select the paradigm, we need to define the certain output, for example, just departure delay, just arrival delay, the overall delay at an airport, and so on. And then we can apply the model, do the training, validation, testing, and the visualization. And we did this using the TensorFlow library of Google, using a graphical user interface we programmed for this using PyQt. So this is all done in Python, and to comprise all these different steps of the framework. And when we have the model, we can do the analysis I talked before, the reverse engineering, the optimization, and the control aspects. So just to, for this short impression, how could we split up these data using different scenarios or problem definitions? Well, for boarding, it's quite easy. We can say we compare different boarding strategies in our approach. For example, we just use random data or data of random boarding to predict random boarding procedures. Or, for example, just individual boarding to predict individual boarding, or we mix this up to say, okay, we train on different data like random boarding, which has got a wide variety of data possibilities, and then predict individual boarding in the last step. For the scenarios at Hamburg and London Gatwick, it's quite different. In the first scenario, we said, okay, we train the models without any restrictions, so not considering any weather conditions. We don't consider any restrictions considering the operational features and so on. In this second scenario, we said, okay, we split this up to good and bad weather days. So, for example, we only train models which or only use data of good weather days using the ATMAP score and bad weather days using the ATMAP score. And in this third step, we added also similar demand approaches. So we looked up days with a similar behavior in the schedule data. This is one approach to split up the data here to create different machine learning models to different scopes of behavior or different behavior classes at the airports. When we take a look at our airports for our applications, we have Hamburg and London Gatwick. We have different kinds of airports. The capacity is quite similar with 48 flights for Hamburg and 55 flights for London Gatwick. But as you can see here, there's much more variety in London Gatwick. We have much more scheduled flights. We have also a higher delay at the end. But we have at least a different structure of the airport. one runway compared to 2 runways crossed at Hamburg Airport. And also these infrastructure data and the surroundings of an airport are very sensible, for example, to the weather influence, which we need to consider here also in our data-driven approach for this prediction and classification of our delay values. One idea in the first step was to say, okay, when we reduce the weather classes, we may also be able to reduce the operational features. As you can see here, the delayed distribution of London Gatwick also has a very quite spread. So we could say just not using a certain value of time, for example, like 5 minutes delay, but to use classes instead to reduce the dimension of the problem. In the technical report, A Matter of Time, Air Traffic Delay in Europe of the Eurocontrol, we could find this -5 up to 15 minutes delay means on time and doesn't have much big influence on the performance of an airport. So we took this as a base class for our labeling process or for the categorization, and then used the distributions of the data, for example, of the arrival delay and departure delay, to label this data and apply them to different classes. For example, in this example, we can say we have 5 overall classes for the raw data and reduce this problem of the exact prediction to much more like a predictive classification, okay, to predict some kind of delay class and not the delay value itself. So this is some approach we did before, and which is some kind of a prior analysis before doing this machine learning application for the operational features. The other thing is to find the values which are comparable to each other, which means the demands, the stimulus of the system, to find days of a very comparable, similar behavior. So one method to do this is the dynamic time warping process, used to find similar sequences, even if they are stretched or distorted over time, but it's a kind of approach to find similar sequences over time, to say, okay, I want to find 10 days in this example for 1 month with a very different schedule, a very different flight schedule, very different demand in the scope of time. And this is what we applied to use or to make the data split for the operational feature and to compare different demands of the airports Hamburg and London Gatwick. The other thing is the feature choice. As I've mentioned before, we have 12 operational features, but we don't want to use them all, and not every feature is important. This is why one wants to do a feature choice or feature selection in the first step. And we use 2 different approaches here: the recursive feature elimination, which is some kind of supervised approach. You reduce the feature sets and train the model again and compare the accuracy of the models. It's very complex, so we changed this to the variance threshold method, which is an unsupervised method doing prior to the machine learning application itself. To see, okay, is there a variation within the features? If not, it's not really important to the application itself. And we did this to not only the operational features like demand and arrival and departure, because they are given, they are important, but for example, to the META features or to the AdMap features, if they are to see which part of these weather data is important and which is not. So let's go to the model application. We use different model paradigms of supervised learning, machine learning models. For the normal prediction, we used a classical recurrent neural network structure, the long short-term memory, the LSTM. And by using these label data, for example, for the delay values to receive this predictive classification, we use CNN models and some hybrids like CNN, LSTM and convolutional LSTM networks with different structures, as you can see here on the left side of table 3. Then we wanted to derive the best or optimal hyperparameter sets for these models, and we used for this we used the grid search approach. From literature, we get some for comparable experiments, we got some good ranges of hyperparameters which we applied to this grid search and derived some good settings for our neural networks and for our examples, not only for boarding, also for the ATFM examples, considering the batch value, the number of epochs, optimizer, learning rate, and so on. To get some insights into the data, and we call this, in this step, the simulation, because this is some kind, we have trained a model up to a certain accuracy, and then we use this for a testing data set to get an impression of the accuracy of the model as a predictor. As you can see here, for a simple example for London Gatwick and Hamburg, for a prediction starting at 11:20 for 12 time slots, which means for 6 hours up to 70:20. And we split this data up to arrival and departure delays and singular impressions of arrival and departure. And as you can see here, using the mean absolute error, we get some good results, especially for the departure predictions. For example, for the weather conditions, also for the no constraints, but we were not able to get usable predictions for the arrival delay and also for the total delay amount. This is maybe because we have just a local look at our airport, and these arrival delays are very dependent also on the network, on the overall flight network, and not only on the local airport itself. So there was a point where we reduced this data, make this predictive classification, and at least we could receive up to around about 60% accuracy for the multi-class classification, and for binary class, which means we just have 2 classes of punctuality. This is on time and not on time. We could at least receive 27% for the arrival predictive classification for a 12-step time horizon. So the last step is now to do some kind of reverse engineering and to say, okay, I have my trained neural network and I want to receive some information of this network. The first step is to get impression of the feature importance of within this trained model, within this trained virtual ATM system. So for feed-forward networks, it's quite easy. We just have to extract the parameters of the network, and we can get some impression of the feature importance. For recurrent neural networks, it's we have to treat them as kind of a black box, and we need to take some other methods. We used the permutation importance, which means we could change the different features and could see the accuracy of the model at the end to get an impression which influence has one certain feature here. As you can see here for the example, London Gatwick, for good and bad weather day. For the bad weather day, we have some influence of wind speed, temperature, visibility, wind direction, and also, of course, of demand and the number of departures. When we go to a good weather model, we have a very small influence of wind speed, wind direction, more like only the operational features, because the weather features are not quite important for these cases. And another method for this reverse engineering or this control aspect, we also want to use the trained model to receive certain input data, for example, to reduce our output data, which is our delay. So we can create this loop. As you can see here, we have our input data. We like to give some restrictions. For example, you have to fill up a certain demand, or you can just switch a demand from one time slot to another with 10% deviation or something like this. So we have some restrictions in the system. We use the trained neural network, and then we use different solutions for this and try to catch up some candidate solutions and try to move the input set to a very optimal output set. So for this, we used a metaheuristic or a nature analog approach, the particle swarm optimization, the PSO, here for this 12 time slots for 6 hours, using the demand comprising the number of departures and the number of arrivals, and to receive a more optimal or an optimal input set to reduce the delay. And this is what this looks like for an example here. PSO results for London Gatwick for 6 hours, 12 time slots. We have our original demand, original scheduled data for every hour here summed up, and summed up 594 flights for 12 hours with an average delay of 13 minutes, 0.44. And using this particle swarm optimization, changing the input sets with a different restriction or different possibility, how much is it possible to change every slot, we get a summed up number of 599 flights with an average delay of 10 minutes. So of course we need to consider the errors of our model in here, but this is one possibility to use very complex network structures to receive more knowledge and gain optimal input sets for such an application. And this is what I will end my presentation with. So we're able to use this framework and these different steps to make prediction for our data-driven models for procedures, performance-based procedures like ACDM, and especially for a very microscopic view like the boarding process. We faced some problems, for example, like the arrival delays, which were very hard to handle and to predict, as they are influenced by many other factors, especially of the whole flight network. So it would be very interesting to apply these approaches not only locally, but also to the network or airspace at all, and also to expand the data sets we have, especially of the operational side, as we reduced our operational inputs to three features: the demand and the number of arrivals and departures. And of course, it's very interesting to see how robust these neural networks are. We worked with adversarial examples, which showed promising results, but we also want to face our research on the stability studies here in the future. So many publications were there, but I don't want to bother you with this. Thank you very much for your attention.
Thank you very much, Stefan.